91st birthday, I should be. Well, but he's not 91 yet.
Each year is actually a superposition of both years, so.
Oh, that was excellent, yes. But yeah, that was excellent, sure. Okay, well, let me talk about what I want to talk about, which is the tension between classical and quantum reality. I have to say also what I mean by those terms. I think that's okay. Well, let's just see if I can get that sense of disruption to go on. Okay. Now, there are two ways in which the quantum state is supposed to evolve on mechanics. The normal way is by the Schrödinger equation, or unitary evolution, or whatever you want to call it. That's the standard evolution process in quantum mechanics. But the trouble with that is it doesn't really tell you what the world does. You have to change your mind occasionally and collapse a wave function, and then you get a load of probabilities for what the universe might do. It doesn't tell you which one of those will happen, but that's the way we use quantum mechanics. So that's the sort of issue, that's the way we do it. Doesn't quite make sense as it stands, because the question is why doesn't the universe behave unitarily all the time? Different people have different views on that. I have a specific view which I'm going to try and explain. Before I get to that, let me talk about the quantum superposition principle. If A is a quantum state and if B is a quantum state, then you can produce a whole load of other quantum states by multiplying each by a complex number and adding them those together. Usually one's only interested in the state up to proportionality, and so it's the ratio of those two amplitudes, alpha and beta, that you're concerned with. But the ratio of the amplitudes gives you the probability of either A being the result or B. When you make the collapse of the wave function takes place, that's what happens. Why it happens or whatever is another question. But certainly these complex numbers fit in extraordinarily well with the geometry of space-time when we're talking about spin. Here I'm just referring to a spin half particle. This is of course very well known to people here. If you take the two spin states, which you can choose to be spin up, that is right-handed about the upward direction, or spin down, in other words, right-handed about the downward direction, or left-handed about the upward one, then for a spin half particle, those are the two alternatives. But all the states are complex linear combinations of those two. It's always fascinated me how these complex numbers, which are purely to do with the way that quantum mechanics works, but they also relate to the geometry of space-time, or space here, because the three-dimensional analysis of space, or this two-sphere one's talking about, the opposite directions of spin, come about as a kind of Riemann sphere, being described by the ratio of two complex numbers. So that's a bit of magic with the way that quantum mechanics relates to the geometry of the world. Now I want to talk about the main principle of general relativity. The principle of superposition is the sort of founding principle of quantum mechanics, and we have a principle of general relativity, which is the principle of equivalence. That's the Galileo-Einstein principle. Here we have a picture of Galileo's conception. You probably never actually dropped a big rock and a little rock and a leaning tower, but this is what the picture is illustrating. So the point about it is there's an insect falling on the big rock, saying, looking at the little rock seems to be hovering in front of it, and the basic property is that you can cancel out locally the gravitational field by falling freely in it, which is an amazing insight on the part of Galileo, and it's the foundation stone of general relativity. Can you have a view? Of course, you can get rid of the gravitational field locally. It's easier by dropping considering accelerating field, but it doesn't get rid of the gravitational field in New York. So you have to have problems, how the two things together, and that's what Einstein managed to do. In the bottom picture I have the same sort of thing, but now with space traveler and a rather futuristic space station up there, and the space traveler and the space station seem to hover, even though the Earth is sitting right there, and locally you can cancel a few out. So that is the fundamental principle of general relativity, which you have to combine also with the principle of special relativity, in other words, in cosmic space, as being the local structure. You figure it all together, it's just space. Okay, now, what I want to try and say here is that there is a certain tension or contradiction even between these two things, which let me try and explain here in the slide. I'm imagining here that you're performing or considering an experiment on a tabletop in the lab, and I'm not considering general relativity as yet, I'm talking about Newtonian gravity, because that's, you're trying to do a quantum experiment, and in this quantum experiment, you want to take into account the Earth's gravitational field. And there are two ways you might do this. One is you use the green coordinates, which are you put a term in the Hamiltonian to represent the gravitational potential, and this gives you the effect of gravity, and you just plug away. Just in the same way as anyone else would treat any other force in quantum mechanics, put a term in the Hamiltonian. Okay, that's one way of doing it. And the other way is the way that if you see Einstein sitting in the corner of the room, you say, you sort of look embarrassed, and then you say, oh, well, no, you should really consider that you could get rid of the gravitational field by falling freely with it. So what I do is I choose the purple coordinates, and those coordinates are the ones which are freely falling in this uniform gravitational field, and having in this yellow box the relation between the two, and I just work cancel it out. I just need to work out how the two ways of doing it are, what's the wave function look like, how they're related. Well, they are almost the same. What I mean by almost is they differ just by phase size. That's the thing you can see in the middle line there, or the line of equations on the left-hand side, where you see the purple Einsteinian way of looking at it, if you like, and the green Newtonian way of looking at it, and the relationship between the two is simply a phase size. And you might say, who cares? You're only going to square moduli anyway to work out probabilities, so we don't care about it. Then you look a little bit more carefully at the phase factor, and you see that it's the strange one. It involves an exponential of the time cubed, the term in there, and you might say, well, even though it's harmless to have a phase factor which is different, it's not a totally harmless phase factor. Because what it's telling you is that the green and the purple way of doing it differ, they really are different quantum vacua. The green vacuum is a different vacuum from the purple vacuum. So that's, again, that's not quite as equivalent as about before. Nevertheless, you might say, who cares? You're going to square moduli, and in fact you're working in a different vacuum. Stick to your vacuum, stick to one, stick to the other, and you get answers which you really can't tell the difference. Okay, I'll go along with that, but at this point I will modify the experiment. In this experiment, I'm considering, as part of the experiment, there is a lump of material, as indicated by this spherical blob at the bottom, which is put into a superposition of two locations. So as part of the process, the quantum process you're looking at, you have a lump which is put into superposition of two locations, and you just chug away as before. Well, you have a little bit of a problem here, because if you're trying to use the Galilei-Einstein philosophy, and to try and get rid of the gravitational field by free fall, you can't really do it, because when you get close to one of these lumps, the gravitational field of the lump is contributing to this gravitational field, and the one in superposition is contributing differently. So you don't really have a consistent way of doing it. So you're stuck. But you shouldn't be stuck, because after all, we believe that the Einsteinian approach is really the correct one. Ultimately, you've got to fit it into the theory properly. Let's see a way of doing it. So what I'm doing at the moment is not trying to produce a high-bar theory, which does incorporate the principle of equivalence in a genuinely quantum mechanical way. I'm trying to do the best I can which is to notice that there is a slight error when I do my calculation, which is that the error is involved in doing it not by free-falling as I go, but I'm trying to do 2 free falls at once and then in different directions. And so if I calculate this little error, I regard it as an uncertainty in the calculation I'm doing, and then I integrate that over space. And I integrate that over space, I'm doing integration by parts to go around a little bit, and I find that if there is the error quantity, which I consider as a sort of disturbance, I integrate that over the whole space, and I get a total error, which is the thing I'm calling E sub G, and that, after I do my integral parts, I find that it's actually an uncertainty in the energy of the entire system. So I claim that the Einsteinian perspective on this leads you to an energy uncertainty to the whole thing. And then what I do is I apply the Heisenberg time energy uncertainty principle, a bit like with an unstable particle. An unstable particle, it has a lifetime, and that lifetime is reciprocally related to a little bit of an uncertainty in its mass, or its mass energy. So here, the mass energy of the system has likewise a little uncertainty, which will be reciprocally related to, I claim, a lifetime of the system. So the argument is that if you want to try and marry these two theories appropriately together, you are led to considering that there is this lifetime to a superposition. You can say that you might argue in a different way here, but I feel that this is a fair indication that this superposition will be like an unstable nucleus, will have a lifetime. And it will decay, state of superposition of two locations for the body, will decay in one location or the other location where this sort of error term disappears, for each independently, and so I see that this has a lifetime. So I consider that quantum states, which involve a mass displacement of this sort, will naturally have a lifetime in order to come to terms with both general relativity and quantum mechanics at the same time. So your claim is, it's a sort of opposite thing. See, people tend to argue that if you want to bring quantum mechanics and general relativity together, what you have to do is quantize gravity. And I can see the case for doing that. But the trouble with the case for doing that is it doesn't really show up until you have circumstances which are way out of any kind of scale of experiments or anything you can consider. It might be relevant inside a black hole, when you have black hole and the curvatures are likely to diverge and become horribly infinite. In fact, they become very horribly infinite. They tend to oscillate in very, very complicated ways with the expectation. You have a very complicated thing, but they diverge definitely to infinity. So your quantum gravity theory, sure, that might deal with that situation, but this is something much more imminent, something that we have to worry more about immediately. And it's, my point of view is that you might say that gravity needs correction by quantum mechanics, but what I'm arguing for here is the opposite thing. That quantum mechanics needs help from general relativity, because it produces these superpositions, which, when it comes to macroscopic superpositions, they don't really make much sense. And so you want to say, well, maybe it's not quite correct. Quantum mechanics needs help from general relativity. So it's more gravitizing quantum mechanics rather than quantizing gravity. So that's the argument I'm trying to make here. Okay. Anyway, what is this energy uncertainty? It's thing I'm calling EG. I put this forward, having done this calculation which I showed you in the previous slide, before realizing that Linus Dioschi had already come to the same expression before me, I think a couple of years earlier actually, and he had come to the same formula for the length of time that superposition should persist. And there's another way of describing it. I can't quite see what I'm saying. My eyesight is not good enough to read my own slides, I'm afraid. But the argument is that this EG, which I've just told you how to calculate, can be interpreted in various ways. It can be interpreted as, if you imagine your body is in superposition of two locations, you picture the body originally, two bodies of the same identical bodies, each other with the same mass, same structure completely, and you imagine they're on top of each other, you pull them one apart away from the other by linear displacement, one away from the other, and ask how much that would cost you in energy, considering only the gravitational field. Of course, the nuclear forces and electric forces and everything would completely dominate, but I'm not ignoring, ignoring all the other forces. I'm considering only the effect of gravity on pulling one away from the other, though there will be a slight force pulling the two together as I get them slightly separated, a slight energy it will cost me to pull them apart, and that energy it cost me is exactly the EG which I just talked about. So then in calling it energy uncertainty, so it gives you a picture of what that EG should be, and gives you some feeling for how big it should be. It should be very, very tiny, I should say. Even for a Planck scale mass, it's very tiny. What's the Planck scale mass? I mean, people tell me it's something like the mass of a flea's eye. That's less than a flea's eye. And that mass is about the Planck mass. But then if you put the Planck mass in this, you put it away from itself, about Planck distance or something, whatever it happens to be, then the time scale for decay will be a Planck time. Planck time is really, well, let me see, it's a lot longer than most particles of this time. So I'm talking about something which pretty big on this sort of scale. Okay, well, let's move on here. The numbers in this picture are off. That's all right. Okay, well, we're considering the superposition EG, then something I've already said. Well, another way of putting it, the gravitational self-energy of the difference between the two locations. So if you consider the one location of the positive mass and the other one is negative mass, and then you look at the self-energy of that difference. That's another way of looking at the formula. Okay, well that's fine in the formula. It would be very nice if somebody did an experiment to test whether it's correct or not. There are various projects, which I know of. They're all fairly far away from seeing this effect so far. There's one which I'm particularly interested in, due to Yvette Fuentes, and she's actually to try and measure the uncertainty in the energy of the system directly, rather than looking at the decay into one or the other, which is a little hard to see. Maybe you could measure this uncertainty directly. It would be a step towards looking at the displacement to see actually whether it does decay into one or the other in this kind of time scale. But experiments currently are a fair distance, not hugely far away, I mean maybe 10, 15 years away, who knows? And maybe the experiments will be done for that long. The picture here is now looking at this in another perspective, from another point of view. I'm thinking now of a space-time picture. Time is going up the picture. At the bottom of the picture we have the body in one location, that's the vertical line there. It then is put into a superposition of two locations. Those two locations separate into location Q and location Q star. And one considers that the criterion of collapse has more or less occurred in that time scale in the picture, so it should become either location on the left-hand side or the location on the right-hand side. Now there's a problem here, because in this picture, I suppose that this Q star, which is the one that survives, and the Q disappears. Now the trouble with this picture is it's not realistic. And because I've indicated there were two other observers, well, they're not really observers, it's like, but people considering, theoretical observers, considering the situation from two different perspectives. One of them is moving rapidly to the left, and the other is moving rapidly to the right, at a significant fraction of the speed of light. And the T ones, which are the or what you might call it, moving rapidly to the right, and those are the simultaneous basis for the one moving to the right one. And you can see they're tipped over, and if the picture that I presented here is the correct one, that the body at Q disappears, and the one at Q star becomes the whole state, Well, you see, according to the one, this observer, the Q star has already disappeared before the Q star has become a host state. So it's not going to be a host state, right? There's a chance that it might disappear, and then the whole thing disappears. That's ridiculous. That can't be what happened. Look at the other observer. The other observer is moving off to the left. And that observer is the S one. They agree on zero, but at S1, the Q star one will become the host state before the other one has disappeared. So there's still a chance, according to that observer, that the Q will persist and might become the host state. That doesn't make any sense. It's got to go. And you can't have it disappear consistent with relativity. There is one sort of loophole to this. I don't think the loophole works, but it's worth thinking about. That is that there is a sort of amplitude attached to the two sides, which they're not normalized. And this amplitude jiggle around. It's a bit like Philip Pearl's Gambler's Ruin. The Gambler's Ruin is that one of them they're sort of gambling against each other. One of them gets so much more money than the other one that you consider it really as the whole stake. The whole amount of money has become that one, and you can ignore the other one. So the point of view is that maybe the amplitudes don't have to be normalized, because that's non-relativistically. If the amplitudes follow the lines, they're not normalized, but one of them might become much bigger than the other, and if it becomes that much bigger, you think, oh, well, maybe the state is reduced. I don't think it really works, but it's worth thinking about. There are problems against it, which I think I won't go into, but if anybody wants to ask a question about them, I might be able to resurrect them. Anyway, what do I think is the answer to this? The answer to this is that the collapse goes right back to the point O, that if the collapse is the Q star, not the Q, it's as though that had happened right back at the beginning. That means, now this is what I'm talking about now, is the classical reality of the situation. And I'll explain that a bit more. The classical reality goes back to the bifurcation point. The quantum reality hangs on to both states in a certain way. Let me continue and say what I mean by these two notions. Quantum reality is a notion which really I borrowed from Einstein, or adopted from Einstein. He had this idea, which I've just stated here, if without disturbing the system, you can perform a measurement which gives you an answer with 100% certainty that one thing is true, then that gives you an element of reality to that state. So this is the Einstein dictum, I would say, for considering reality. Now, the thing about this is that in the view I put it forward here, this has to be what I'm calling quantum reality. Quantum reality is indeed the Einstein dictum. If you can say that is an experiment which you can perform, which is without disturbing the system, and gives you an expected answer with 100% certainty, then that is as a notion of reality. That is a notion of reality. But I'm calling it quantum reality. It's reality that we have already in this picture here. Suppose you have a spin half particle, or a spin half atom or something, and you say that it's your calculation of where the spin should be pointing is, say, off to the right, just at the angle indicated in the picture. Then you can perform an experiment to measure whether it's in that direction with 100% certainty. So that gives a reality to that particular spin measurement. But if you don't know it, you can't tell. You can't say, system, what is your spin? It looks at you blankly and says, I don't answer questions like that. What you can say to a quantum system is you can say, is your system, spin of the system, pointing up to the right in the direction indicated in the picture? And then the system, if you got it right, it will say, yep, you got it right, with 100% certainty. If you haven't got it quite right, it may most of the time say, yep, you got it right, but a few times it'll say, nope, you got it wrong. So that's the distinction between it. It's not, you haven't got it right, then it won't give you the answer with certainty. But quantum reality has this curious feature. You're not allowed to ask the state, what is your state? What are you? What is your reality? But you can have a suggestion of what you think it might be, and you can test that suggestion. If you're dead on, you'll get 100% confirmation that it is right. So that's the idea of quantum reality. Classical reality, you can ask the state, what is your state? And the system will say, my state is X. Yep, that's fine. Quantum reality, no, you can't do that. You can only say, is your state X by any chance? And if you got it right, it will say, yep, my state is X. Or before measurement, it's X now. If you made it wrong, it would say, my state is X now, yes. A moment ago, it was a little bit different from that. But you hit it lucky, and you got the right answer. If you chose the opposite state, you get it wrong. Okay, that's how classical and quantum reality work. In this picture, I'm trying to indicate the interplay between these two types of realities. At the bottom picture, I have a laser aiming a high-energy photon. It hits a beam slitter or hot filter mirror or something, and the state is split in two. Half of it goes down with the picture, the other half hits a little grain of sand or something, or seed eye, or whatever you like, and if it's, well, it puts it into a superposition in two locations. And then as you move up the picture, you see the progression of time. The quantum reality of the state becomes that superposition. Eventually, it becomes, collapse happens, becomes one or the other, but the space-time has this continuous trajectory of following the left-hand path. It's as though the right-hand path, as far as the classical reality is concerned, never existed. It just follows the left-hand path, and the right-hand path is as though the reality is never there at all. There is a connection, I don't want to go into this part of the story here, but in my view there is a connection with conscious experience. And conscious experience is sort of probing the top of this picture. And it does maybe give you a reality in your own experiences to the quantum reality, but it doesn't persist. It doesn't persist in the classical reality. It's a more robust kind of reality. The quantum reality is there. It has a governs the classical reality to some degree. It's a bit subtle in that perspective. I thought it was interesting to look at the EPR situation. Here, I'm considering the normal kind of Alice and Bob thing, where we have a spin zero state at the bottom, time going up the picture as before, and Alice is the left-hand trajectory, the thick line going up on the left, Bob is the thick line going up on the right, and they are handed a spin zero state, which is split into two spin half states, keeping the quantum state properly as it should be, as a quantum state. The Alice on the left has her state, and as further up her world line, you'll see the top point on her world line. She performs a measurement on the state, and she tries to measure it, let's see what the picture says, I think, up towards the right, she measures it that way. And the answer she gets is no, the other way around. So according to her measurement, afterwards, on her world line, she knows that the state is downwards to the left. Okay, we've got Bob. Bob, at sort of time, a little contemporaneous with Alice. This was later in the frame of reference I've got here, but they're space-like separated. Bob makes a measurement, he measures it up-down, and he then, he doesn't know what Alice's measurement was. She can't send a signal to what her measurement is, and she can only send signals along the future world light cone, along the future light cone, and that hasn't got anything. So that's just as well because she's run into horrible contradiction. This case. However, if you look at the quantum reality, it's very curious. The quantum reality of this picture is indicated, of the whole situation is indicated in the picture. Right at the bottom, you have the quantum reality, it's simply spin zero state. It's an entanglement between the left and the right parts, with an entangle. But then you move your way up, and the Bob on the right makes a measurement. No, the Bob on the right receives what you see on the backward cone. It's rather curious. And it has to be on the backward cone because you can consider observers moving with almost the speed of light in different directions and trying to make a picture of what's going on. And you find that this picture requires the quantum reality to propagate backwards along the path light cone. So that Alice's measurement at that top point on the left-hand curve projects backwards along her path light cone, hits Bob's word line at a point down there, I think I've got to call QB, and so that changes Bob's state to be the opposite of the state which Alice has obtained by her measurement. She's obtained, by getting it wrong, the state being downwards to the left, and so Bob's state must be upwards to the right. So Bob's quantum reality of Alice's state is down to the left. You can't measure that. If you could measure it, then you'd of course have a contradiction with communicating with the speed of light. The curious thing about quantum reality is it can project backwards in time in this way, not quite backwards in time, but along the path light cone, in this kind of way, and because Bob is not able to access this quantum state that he has now, according to quantum reality. Quantum reality is, yeah, this state is already telling you what Alice's is, and therefore what your state is. But it's no good because you can't ask the state. Because quantum reality can't ask the state, what is your state? You can't do that. You could just try to guess, and your guess works out. If you got it right, or if you're close to getting it right, it usually works out, and that's how it works. So I think this is a pretty consistent picture. I was rather struck by how consistent it is. I haven't worked it out for 3 different observers and all that. I rather think it's consistent for any number of them. So this is showing you how quantum reality behaves. It behaves in a pretty strange way with regard to our ordinary experiences of how things behave in causality. Okay, well that's basically the end of my talk, but I did want to bring in something else in. This time here I was talking with Chapman, and there are people here who are very keen on one of Jackie's ideas, quite rightly so. And one of the things that they talk about is this rather remarkable idea of the bomb testing experiment, the Ernst-Weidmann bomb testing. So here we have a bomb, and it has this extremely sensitive detector on its nose, and it's so sensitive that if you hit it with a single photon, it will set the bomb off. So on the right-hand side, you see what happens. The bad news is that the bomb has been hit by the single photon, and off it goes. The trouble is that you have a big collection of these bombs, and occasionally we get a dud one. The dud bombs are such that the detector, and it's very sensitive, it happens to be jammed. And so when the photon hits it, it just gets reflected off and the bomb doesn't go off. So it's a dud bomb. And we have the dud bomb illustrated on the left-hand side, and the genuine bomb on the right-hand side. And the problem is, you've got a whole pile of these bombs. You know that some of them are dud. You want to find the bomb in that pile which is a genuine good bomb. And the way of doing it is very remarkable, except a press the button. Here we go, that's the answer. You do a experiment, you put the photon in two like this, and you put your know that you have the big bomb in this nice concrete thing that even if it goes off, it doesn't hurt people outside. Nevertheless, you can tell if it's gone off or not. But the bomb should be attached to the mirror on this anyway. And so as the photon hits it, if the bomb is dud, then it behaves like an ordinary mirror, and the two things simply go here together, and A always receives the photon. However, if occasionally you see that B has received the photon, but the bomb has not gone off, this means that the bomb has actually measured the photon, but it's not gone off. Right, make it the right way around. If it's a genuine bomb, it If it's B, if it's B, it should be, if B receives the photon and the bomb's not gone off, then you know it's a genuine bomb. Is that right? I hope I said it right. So, anyway, I was going to leave this with you. The point is, I want to leave it really as a sort of puzzle. So how, I don't know the answer to the puzzle, I'm just putting it. How do we think of the classical and quantum reality situations in this case? There is an issue here, because the bomb going off, it may take a little while to go off, and it won't go off before the photon has been reached by the detector D, or the A, or whichever way it is. So maybe the detector D will receive the photon, even though the bomb is in the process of exploding. And because explosion takes a little while to happen, does that influence the fact that whether B can receive the photon or not? Needs thinking about, and I'm sitting presenting this as an example to think about. How does the timing of when the bomb goes off affect whether B or A can receive the photon if it is a genuine bomb? Thank you. Thank you very much. So happy to answer any questions for that.
Avi, be sure to press the...
Sorry?
Avi is coming down.
Should I come down?
I think so. It does that. Yeah, now it does that. Yeah. Now it's howling to do that.
You have to press your microphone, otherwise he's not going to be able to enter.
Yeah, no, it does exactly high off the microphone on the left of it. Yeah, that's why.
I think Roger may need to mute himself while the person, so there's no feedback. I'm not sure if that's what's going on.
Roger, can you hear us? David, I would suggest you mute yourself while we speak into our...
No, okay, Les thinks I'm wrong, he has more experience.
The podium.
This microphone is here, and this is the microphone. Just speak there. No, just speak. No. Close this and speak here.
Yeah.
Speak.
Yeah. Close that microphone.
Yes. Just speak inside.
It won't work.
Now the bomb is.
I don't know if that webcam's microphone is going.
The only audio is from here.
Okay, try it now.
Try it. Ask it if you can hear.
So Roger, can you hear me?
You have to turn on the mic.
Turn on the mic. Turn this on.
Yeah, but then
Yeah.
Yeah.
So it's not on, whatever you say.
It's on.
Hello? Sir Roger, can you hear me?
You should turn off the
I can hear you.
Yeah.
Can you hear me?
Yeah.
Good.
Turn off the Zoom.
Can we get rid? Can we get rid? How is it now?
Wait, we can't hear you.
Ah.
Turn off the speakers here.
No yet.
I didn't hear that. If you were saying something, I didn't hear it.
Okay, try it now.
Now the
Hello.
bomb is on.
Hello. Sir Roger, can you hear me?
I can hear you.
Okay. Thank you very much on behalf of Weidman and myself for doing this great public relations to the bomb. And 30 years later, there is still differences of, between Lev and me, who is in the audience and can comment later, about how we see this bomb problem. May I remind you that some 30 years ago, when we first met, you presented in Temple University a much simpler question. And I confess that that question was the motivation for us, for me at least, for thinking about the bomb experiment. You showed a photon hitting a beam splitter, and then it goes to one out of two detectors. And then one of the detectors clicks, and the other is mute. And then for me, it was taking Einstein's relativity theory, the Lorentz invariance, and then I realized that the silence of one detector, just like the click of one detector creates the silence of the other detector, it's the other way around, that the silence of one detector gives rise to the click of the other detector, and from this we proceeded to the bomb. However, you did something very interesting. You time reversed it. And then when the photon came back to the beam splitter, to the half-silvered mirror, in some of the cases it went to the wall. As you remember that. And you say there is something wrong with the time reversal. All I want to say, first of all, thank you for your dealing with the bomb, and thank you for showing something very interesting, and that is that if you make, in the Mach-Zehnder interferometer, if you make only one of the mirrors loose, only one, the other remains fixed, then if the mirror moves, of course, interference is destroyed. If the mirror does not move, then interference is also destroyed, because it is movable. And the question could be, how could the photon know that the mirror is loose or not? It's just a dumb photon. The answer is interesting, and it has to do with your question some 30 years ago. It turns out that even an impossible past, I mean, when one of the detector clicks, then you have two futures. One of them becomes real future, and the other becomes fake future. But you, some 30 years ago, showed that there is also a fake past. If it goes to the source, it is a real past. If it goes to the wall, it is a fake past. What I want to tell you is that we are fortunate by the inspiration of Yakir to show that sometimes you can get a real physics from the fake past, not only from the fake future, and that there is a beautiful variant of the bomb testing experiment which Lev created. This is the nested interferometer experiment, and there you can see that where fake future and fake past meet, sometimes you get a real particle that you can detect. It didn't go there on that arm, it didn't come back from that arm, it is just there. I would love you to attend this lecture or hear it on Zoom, and my coming down here was first and foremost to say a great thank you for the introduction that you wrote to our book on quantum mechanics, and for your dealing with the bomb experiment, and above all for you, Sir Roger, for being there. Such a great source of inspiration and courage. Thank you very much.
Thank you for the bomb, which is a fascinating idea.
Anybody else? Yeah, but you have to use.
You're doing it.
There wasn't a question attached to that, was there? I've forgotten it all.
Yeah, now is
Ready?
Thank you, Roger, and so thank you for presenting the second picture of the bomb tester. This is how I like it. When it's okay, then it's present, and when it's not okay, then it's not present. But I want to ask you about conceptual thing. You think there is a quantum reality and there is a classical reality. And I fully believe only in quantum reality, and I believe that I'm a quantum object. So if I'm a quantum object, I probably know who I am. You said that when I'm a quantum, I kind of cannot ask in which state I am. So would you say it's not consistent to believe that everything is quantum, or if you want to believe that things are only quantum, how I will consider myself? Do I know in which state I am, or am I allowed to ask in which state I am, or how to consider this?
Are you taking a many worlds view on this?
No, of course, you know.
Sure. If you say it's entirely quantum, then presumably you're led through a many worlds picture.
Yeah.
Is that right?
Yeah, yes, of course, you know. Yes.
So then the other view would be presumably that your experiences are just one out of many parallel experiences or something of that sort. Is that the sort of picture you take? You see, I have an opposite view on this. I have a view which is more or less that, yes, once you go through a stage in life where you believe in many worlds, but then you shouldn't get out of it. My point of view is that quantum mechanics, as I presented in my talk, that quantum mechanics is not perfect theory, that it's actually, in a certain sense, incorrect. I mean, we don't mind theories being incorrect, you know. Newtonian theory is incorrect, it's an amazing theory. You know, general relativity is incorrect in a sense. Schrödinger and Einstein were much more polite. They were saying it's incomplete. And that's to say that you have to add something to the theory. I think you can't really add something without subtracting something at the same time. Something about the theory isn't, in my view, correct. So I'm not taking the line that you're taking, which namely is that in sense you've got to make it correct. You've got to say that all these different alternatives coexist, and therefore we are led to a many worlds type picture. But then I have a lot of trouble making sense of consciousness, if you like. If my conscious experience goes along one track, what happens to all the other tracks? Are they zombies? Are they other people who have experiences like mine, but they're not me? What happens to all my friends? I worry about them all very different tracks, and I'm all left behind in certain sense. I can't make a consistent picture out of them. And so I prefer to take the view that quantum mechanics is limited in its precision, and this limit has not yet been reached by experiments, but in the next, I don't know, let me guess, 10 to 20 years, within that period of time, we will see experiments which go beyond current quantum mechanics and tell us that the collapse process is an actual physical process which takes place in accordance with the conundrum which I presented earlier in my talk, which is to show that there is a conflict between the principle of equivalence of Einstein's theory, which is the main building part of the theory, based on the principle of equivalence, the Galileo-Einstein principle, and the quantum principle of superposition. They don't live together, so I'm trying to argue. They almost do, and if you're looking at mass displacements which are very tiny compared with Planck scale, well, much, much tinier than Planck scale, you just don't see them. You don't see the effect of the collapse of the wave function, which should be occurring all the time, which is giving us a fairly reasonable classical picture of the world, which works very well. It's hard to see why classical physics works so well, put it like that. If you take a view that quantum theory is really, all these superpositions do coexist, why do we get such a wonderful picture which works so well, which is the classical physics world? And I don't see any explanation.
Thank you. Just maybe remark that I think that you are conscious in all parallel worlds. So there are many Rogers with many consciousnesses, and I think it is consistent. And
I'm not going to jump in that direction, but okay. Yeah.
yeah. Okay. Thank you.
So Roger, so first, thank you for the very interesting talk, and for me it's very exciting. You talked about consciousness. Now, we know that we cannot quantify consciousness. And on the other hand, if you can think about universe that is full of water, for example, you cannot define this water because it is everything, right? For defining something, we need to define by other things, described by other things. What I want to say is that maybe it will be possible. What is your stand about that everything is consciousness, and from there we get the matter world?
Well, I don't think everything is consciousness. I mean, I think there's consciousness. Well, you see, there's a concept which sometimes we refer to as proto-consciousness. You see, you might say that there's a potential for quantum consciousness all the way in all. Whenever the collapse of the wave function takes place, the argument goes, this is associated with an element of what we call proto-consciousness. But it's not genuine consciousness. The scheme that Stuart Hammeroff and I tried to develop, which we call OR, OR stands for objective reduction. It takes the view that the reduction of the quantum state is an objective process, and it occurs when the mass displacement is the sort of argument I was making. So it's certainly in opposition to the view that we were just hearing a moment ago, which the quantum simply don't see why we need to take that view, because why should quantum mechanics here? That's not what you're raising, it's a question. You're raising a question of quantum, well, quantum is being, I'm not quite sure how you would put it, that it's sort of everywhere, are you saying, but it's not everything. How would you say it?
No, I mean that,
it's not a,
that the foundations maybe.
Is there any consciousness on the moon? Okay, there was at a certain time in Penrose's history, but rather few compared with the history of the moon altogether. But do we say that there is consciousness on the moon? There might be a little bit of proto-consciousness, you see, because whenever the reduction of the state happens, according to my view, there would be the building block of which consciousness is constructed, which is the proto-conscious building block. But to make a building, you need more than building blocks. You need a construction scheme. It has to be built according to a certain plan, and it probably has to acquire certain features that we don't understand properly. So it magnifies the quantum alternative into something which becomes conscious alternative. Don't be something like that. No, but certainly it's connected to consciousness. But we're a long way from understanding. But there are some interesting new features. Well, they're not that new. I didn't talk about them. I'm wondering about whether I should talk about them in this talk, but I thought it was perhaps venturing a little too far outside. Experiments which go back to the late 1900s, performed by Benjamin Libet. And these were experiments where he has an electrode which is attached to a patient's finger, and the patient is having an operation on the brain for some other purpose, and he is allowed by the patient to perform these experiments, nothing to do with the operation that he's having to do on the patient, but where he either stimulates the finger and notes when the patient says that happened, and it's pretty almost instantaneous, or he stimulates a part of the brain which has to do with the sensory perception of that part of the finger. And there's some curious paradoxical features which come out of it. The main thing is that if you stimulate a certain part of the brain after the finger has been stimulated, and you do this a half a second after, I can't remember if it's half or a quarter of a second, then a quarter of a second after, then the patient does not feel what that patient would have felt had that not been stimulated. But somehow, as though the actual sensations that the patient feels, or anybody feels, is delayed by something like half a second. And this seems to be the case. It's not clear. And it's very paradoxical, because when you think of, say, table tennis, particularly table tennis, I used to play table tennis, you see, and you think you're making a decision, am I going to tip the ball to the right, to the left? And it's based on an instantaneous, very, very rapid choice, judging partly from what you think your opponent is likely to do, and the view is that you're making that choice consciously. According to the standard view now of people who work on the subject, they say, no, all these things are done unconsciously. I don't believe it. I think I did make this conscious choice. Watch tennis players, they're making much more rapid decisions than this. Performers of musical instruments, they may be playing jazz and deciding to improvise at a certain point. Is that improvised decision made unconsciously always? I don't think so. But it does mean that you have to have some of this sort of retroactive aspect to it, which is present in the picture I'm presenting, that quantum reality has a kind of retroactive aspect to it. It does go backwards in time in a certain sense, in that the actual classical reality can be influenced by a conscious decision, which is in a certain effect only projected backwards, and in a certain sense happens later. It's a hard thing to make sense of, but there are experiments. Unfortunately, the limited experiments, I think they're illegal now. the problem is that having a brain which is, I think there may be some way around it.
Yeah.
But I was told by Stuart that those things are not, you can't do that. Which is very shaky, because I think they're extremely interesting. Right?
Yeah. I just
probably got away from your question, but
I just
I
want
do
to
think it's tied in with consciousness. I don't think consciousness should be. See, I'm happy to say that proto consciousness, the building blocks are around, but they're not really made into a building. They're just lying around. To be really genuinely conscious, you have to have these things organized and orchestrated, is the word we use, in an appropriate way, which probably involves a very large number of these conscious proto elements. But we're a long way from that. But nevertheless, maybe at the beginning of that, which is a very exciting place to be.
Yeah, I think that the definition of consciousness is not really rigor. Like feelings and thoughts, there are ancient traditions that said it is not consciousness. It is biology and chemistry, right? Maybe. So what is
yes,
it?
well, you can have problems. But you see a lot of things. Well, you see, Stuart Penrose entering the subject was really through anesthetics. And this is an interesting route into consciousness. What is it that actually turns consciousness off in a reversible way? And it seems to be it's not a chemical process. It has to be something, it's a physical process. Something to do with the different, because the things which have caused general anesthetics are completely unrelated chemicals. Even xenon, I think, which is a nerve gas, is an anesthetic. But there's some process which involves physical procedures, but they're not ordinary chemistry.
Yeah, so it's under time.
Exciting.
If it's a process.
Very exciting subject. Yes.
Okay. Interesting.
But you see, I'm arguing that it plays into some of these curious features of the collapse of the wave function. In my view, it's much more interesting than trying to say that we're all part of one big quantum state, because you get really stuck with that. We don't know where to go to. Whereas if you say, no, there is something happening which we can explore, and it does involve something new, not quantum mechanics, I regard that as much more exciting.
Okay.
Yeah. Thank you.
Roger, we have a question coming up. Just one shameless advertisement. I think that the cutting edge, no pun intended, follow-up to the Libet work is actually being done right here at Chapman. We have a new brain institute. So the gentleman's name is Aaron Scherger. He's an amazing neuroscientist. But I'll send you some of his papers. It really is the cutting edge of the follow-up to the Libet stuff.
I might have concentrated a little more on the conscious angle of it, but I decided not to in this talk, but maybe I don't know what's right about. But if I'd known about that, I might have put it a little more in that direction.
I'll send you some of his papers.
Yes, thank you.
So thank you for the talk. Just a clarification on one of your last slides concerning Alice and Bob sharing an entangled state. As you mentioned, in one reference frame, when Alice measures first, the state update gives a certain state for Bob, and quantum reality then would say that Bob could measure that state with unity probability. But in another reference frame, as you mentioned, that does not exist, and we have a quantum reality for Alice.
Yes.
So would you say that quantum reality depends on the reference frame, or that we just should forget about the validity of quantum reality and just an...
Did you want to finish? If you finish your question, sorry.
Just an additional question linked to that. Do you think that the state update, or collapse as you called it, is instantaneous, or is it constrained by the light cone?
Well, you see, the last part of your question, I think I gave my view on that. You see, it's not instantaneous is a bad idea, really, if you have two separated objects. That was the reason for my picture, the relativistic picture with the two branches going off like this. And you can't say it's instantaneous. That's the whole problem. Because if it's instantaneous, in what frame is it instantaneous? That's why it has to go back to the source. The classical reality has to go back to where the bifurcation took place, which is actually a good thing in another sense, because there are experiments which have been performed. Ransato is experiments performed in Italy, which were supposed to test what they call the Penrose model. I'm saying it's not Penrose part of it, maybe it's the part, because you see, if you're considering that the collapse occurs sort of all the time in a system, it would cause a sort of heating, because there's a kind of jumping. When this collapse happens, and it collapses all the time in the body, then this collapse causes the material to jump in a sense. But it's as though it was being heated. And if you have a kind of model which tries to explain this, tries to accommodate this, put it that way, it has to present this heating. And so we did this experiment by going into a mine shaft or right under the deep mountain to get rid of all these other effects. And they tested to see whether the spontaneous heating happened. And they found it didn't. There was no heating. Now I claim that, in my view, there shouldn't be any heating, because it has this retroactive aspect. The collapse of the wave function goes back to before they separate. So it's not as though the things separate and then it jumps to one or the other, which looks like introducing a heating element, because if your systems start to jiggle away because they're jumping in the sense, that would look like a heating effect. And you can make that explicit in the model. What I'm saying is because it goes back to the origin of the separation, it never heats, because it doesn't jump. So it's not instantaneous in the sense of, okay, space-like slice across the picture, makes it one or the other. But it's instantaneous if you like, might go back to the origin, and then doesn't mean anything to say it's not instantaneous, because that's where the classical reality choice is made there. But that classical reality choice is influenced by the quantum reality. So if you like, the classical picture is completely consistent as you can't send signals backwards and backwards. You can't send reality signals backwards and backwards. But that's in the quantum reality. The quantum reality has this curious retroactive aspect to it. It goes back along the path like that. But it doesn't cause you problems, because it doesn't give you something you can measure. The analysis of information, as I say, would project backwards to a bomb, then she could send a message. And if you can measure the quantum state, the asking has already got her measurement in his quantum state. But you can't measure it. But you could say there is an objective reality which is imposed on the situation by what happens. And maybe what happens later, that objective reality, the objective reality was projected backwards. But it never causes you retroactive problems which you could send signals faster than. That's a key thing, because then you're really in trouble. I hope that's I answered your question, but done my best.
Yeah, Andy is waiting for it.
All right, I think that's the last question. Roger, let's give Roger another warm. Thank you so much, Roger. We have Len Suskin in the back.
Well, thank you for very interesting questions. I think that's very, very worth thinking about.
Okay.
And I'm interested to know that you have people here who are thinking about the consciousness end of it. But a lot of scope for well, ideas and interrelations between. See, it's very different from the old ideas that Wigner and maybe von Neumann used to think, that you needed a conscious observer to collapse the wave function. And that's, I don't believe that one. And I have arguments against that. I can talk to Wigner about it on my occasion. I was in Princeton and I didn't know Wigner. But we had that to hang lots of it. And I was quite impressed that he was not as dogmatic about it as I thought he would be. He was more open about it. He just thought it was a point of view which should be explored, that he cheating. But I don't think it's got much chance.
Yeah, I think I spoke with Vigner near the end of his life. He was still very open to that idea. But anyway, okay, Roger, thank you again, and we'll be in touch. Thank you.
Okay.
Okay.